It's my great pleasure to welcome you all to the first Computer Science plus X Colloquium Series lecture of the year. And it's really wonderful to have Duncan Watts here to get the series off to a wonderful start. Duncan Watts got his PhD from Cornell in theoretical applied mechanics. He spent some time at the Santa Fe Institute. He then moved to New York and was a professor at Columbia University in sociology. And at the same time was a researcher at one of the premier industrial research labs in computer science, looking at the space of computer science and the internet, which was Yahoo Research. He has since transitioned to help found the Microsoft Research New York lab, which is carrying on the great tradition of that Yahoo Research lab in the time. And is also a professor at large at Cornell University. He's one of the leaders in the area between social science and computer science, and one of his early and one of the most influential works in that area is a paper he co-authored with Stephen Sargatz in 1998 called The Collective Dynamics of Small World Networks. This paper has 30,000 citations. So not only is he study it, but he also practices it, apparently. But this paper was published at a time where the two models that people studying social behavior were either very structured models, very regular graph models, or completely random models. And this paper was one of the pioneering papers that proposed trading off these two extremes and discovered that actually you don't have to add too much randomness to the structured model to get networks that have much more similar behavior to the social networks that we actually have. So that was an incredibly influential paper. Another thing that Duncan Watts is well known for is, besides publishing the great papers, but also making sure that the science of those papers is accessible broadly to the public. And in 2003, he published his 6 Degrees, The Science of the Connected Age book, which is how many people learned about this stuff for the first time. And in fact, he continues to publish in popular media. And in our Computer Science 101 class for the last 5 years, we've been teaching using some of his New York Times articles as our source material. In particular, an article that I really love that's entitled, "Is Justin Timberlake the Product of Cumulative Advantage?" Without taking up any more of his time, let's welcome Duncan to this series.
Thank you, Jason, and thank you all for being here. I have a lot to get through, and so I'm going to go quickly, and I apologize if I skip over details. I assure you that it's all the material is available in published form, so I'd be happy to share those details with you if you're curious. So I want to start by trying to articulate what I think computational social science is and why I think it's so interesting and important and salient for this particular moment in time. So to step back a bit, when I think about social science, what is sort of the core of what makes social science social? And I think that it's fair to say that when the kinds of questions that social scientists care about, we talk about we talk about firms or markets or cultures or families or political parties as if they're actors who think things and do things and have intentions. But we also realize that at some level this is a convenient fiction, that really all the things that we're interested in are aggregations of individual people who are interacting with each other in some sort of complex manner. And it's the individuals who have the beliefs and the perceptions and the plans and who take actions. And so this question of how you get from the individual to the collective, this MicroMacro problem, as we call it in sociology, is, I think, really the sort of central scientific problem that we're all trying to grapple with. And the reason why this is such a difficult problem and has resisted advances for so long is that empirically it's very hard to study these emergent systems. That if you want to even just observe thousands or millions of people interacting with each other over extended periods of time, you're already talking about an extraordinary amount of information that you have to be able to instrument and make sense of. And if you want to understand causality, if you want to understand why things are happening, you have to be able to do experiments. And being able to do experiments on people at a macro scale is obviously an even more difficult thing to do, and sometimes and very frequently just impossible. And so if you think about what is the scientific method, you have a hypothesis, you then design the test for your hypothesis, you go and get the data, you design the experiment, and then you check your hypothesis. If you can't do the sort of second two-thirds of the scientific method, it's very difficult to do science. And so I think in social science, what we have done over the last 100 years is really we have generated an enormous number of interesting ideas or theories, hypotheses, explanations for the world. But it's very difficult for us to test them and to reject them. And so I think that accounts for a certain lack of progress that we feel when we compare ourselves to other scientific disciplines. So the reason why this is such an exciting time to be doing social science is because some of these barriers are being lifted. Right? Not all of them by any means, but some of them. There's no secret here. Many people have noted the dramatic increase in data, what we sort of loosely refer to as big data. All this data that has been generated as a byproduct of the kinds of things that people are doing every day, either online or on their phones, or using some kind of digital communication technology. And so we've constructed almost by accident these enormous instruments that allow us to see what people are doing on scale, at scale, but also at a very granular level. And so this data is just intrinsically interesting to social science. A second kind of development that has received somewhat less attention, but I think is also very important, is that web platforms allow us to do experiments of a sort that have been very difficult to do in the past. And so I'm mostly going to talk about the evolution of the sort of traditional lab-style model of experiments, but equally important is the rise of field experiments, the ability to sort of manipulate, to randomly manipulate treatments in a naturalistic setting. And so if you put all of this together, you see this emerging field at the intersection of the computational sciences and the social sciences. And for want of a better term, and I think it's the term that we're stuck with now, whether we like it or not, we call this computational social science. And so that's really what I mean when I talk about computational social science. And for the rest of the talk, I really just want to illustrate it by example. So I'm going to, it's really sort of, my examples will be broken into two parts. One where I'm talking about this sort of idea of big data, of looking at observational data that is found in the world, that is generated for other purposes, and we're using it to try to answer interesting social science questions. And the second half is where we are designing experiments to go and collect the data that is interesting to us. And in both cases, I think it's important to realize that the questions are all old questions. These are questions that have been around for decades, or in some cases even centuries, and that are by no means novel to social science. But what is novel is that we can bring, by bringing new types of data to bear on them, we can make progress that has been difficult to make before. And then finally, if I have time, I would like to discuss briefly, that all is not sort of good in this world. We haven't solved all of these problems, and in fact, some of the progress that we've made has really just sort of highlighted how much more progress we need to make, and I'll try to talk about that as well. So moving right along, I want to talk about using observational data from the web to understand how things spread. online. And so, this idea of contagion is something that many of you, I'm sure, have thought about. I would suggest that when you think about things going viral, when you think about memes spreading or ideas spreading through a network or online, that you have some sort of mental model of what's going on that looks roughly like these two pictures. There's a good reason for that a lot of the mechanics, a lot of the models, a lot of the mental models that we have of contagion, of social contagion, come from the biological world. And in the biological world, contagion, by and large, does in fact look like this. If you think about Ebola spreading in West Africa a couple of years ago, there really is somebody who was the first person who got infected, and that person infected a few of his or her family members or near neighbors, and each one of those infected a few other people, and each one of those infected a few other people. And so over time, you see a very large number of people getting infected through this multi-generational branching process, where at every step only a few additional people are getting infected, but it can grow very quickly, exponentially, to encompass a large population. And so, when we kind of port these models over to marketing or to social movements or to other kinds of applications in the social sciences, we retain this mental model of how things are what is going on under the hood. But very often, we don't have that kind of data. So when we try to study these exercises, just try to study diffusion empirically, typically what we have is something that looks like this, where we have some sort of aggregate count of how many adoptions have taken place over the whole population, and we plot that against time. And so on the left, you have the famous paper by Coleman, Katz, and Menzel about the diffusion of tetracycline in Illinois, I think, among doctors in the Midwest. And on the right, you have the Everett Rogers schematic of diffusion, which shows this famous S-shaped curve. And the idea is that when you see an S-shaped curve, you can say that you can conclude that what you're observing is a diffusion process, that something that starts off relatively slow and then increases exponentially and then asymptotes as all the susceptibles in the population are exhausted. So this is a very common way of identifying diffusion, but the problem with it is that, well, there's two big problems with it. One is that there are lots of other ways of generating S-shaped curves, some of which have nothing to do with diffusion at all. So just because you have a model that generates S-shaped curves, and just because you see an S-shaped curve in the world, doesn't mean that you have justified your model, because all sorts of models can generate S-shaped curves. So the aggregate nature of the data is a problem. The second problem is that we only generate these S-shaped curves when something interesting happens, right? When the social scientists only go and study things after they've become interesting enough to be noticeable, right? So you might think, well, that's obvious. Why would anybody study uninteresting things? But of course, if we want to understand why things succeed, why things spread, we can't only look at the things that have spread. It's like if you want to understand how people become rich, and you only go and talk to rich people, it may turn out that all of them have breakfast, and you think, a common pattern is that rich people have a hearty breakfast in the morning. But of course, it turns out that unsuccessful people also have hearty breakfast in the morning, and it's not a very predictive feature. So if we want to understand why things are happening, we have to have a total sample of the population, in some sense, everything that is trying to diffuse. So the data that we need has to have a couple of different properties. One is that we want to see individual level, person-to-person spreading events. And we also want to be able to look at the entire population of potential diffusion events. And so, not surprisingly, I'm going to argue that this is increasingly possible in an online environment. And over the last decade or so, we see an increasing number of attempts to use digital data to reconstruct diffusion events in precisely this way. And so once we once we have data like this, we can ask questions that are a little different than the questions we've been able to ask before, which is, well, how much of diffusion is really viral? What do we mean by viral diffusion? Can we characterize diffusion in some sort of structural sense so that we know it when we see it? And can we predict it? So I want to talk about a few different projects with my colleagues over the years. This is the first paper with Sharad Goyal and Dan Goldstein, who were with me at Yahoo several years ago. Dan is now at Microsoft and Sharad's at Stanford. And we took really just a convenient sample of projects that we had worked on or that our colleagues had worked on that were motivated by all kinds of different original ideas, but all had the common feature that there was some notion of social referral built into them. So, maybe it was a video viewing app where people could synchronously watch a video and chat with each other, or it was a Facebook survey, network survey that we ran where we were interested in people's political beliefs and how similar they were to their friends. We also worked with the Yahoo philanthropic group to build a kind of pay it forward social good campaign around the holiday season. So these were all very different projects. They were different. They were involved different populations. They had different referral mechanisms. They were spreading over different networks. There were different incentives involved, and the diversity of these projects was actually the point. Because if you take any one of these projects and you studied, how did things spread on Facebook, someone could say, well, Facebook's kind of weird and it's got this sort of very heavily biased population, and so what you find doesn't generalize to anything else. And if you study Twitter, you could say the same thing. And if you study, if you study a video a viewing app, you could say the same thing. But if you study all of these things and you find consistent empirical patterns across all of them, then you have at least a stronger claim that your results are robust with respect to these different biases. And so what we found was remarkable similarity across these different domain-specific applications. So here's the 6 applications that we looked at, and what you can see represented here are the 5 most common cascade structures, or motifs as we call them, that we saw in the data. So just take the Twitter one on the top right-hand corner. This is what we are studying here is 40 million instances of where someone has introduced a shortened URL into Twitter, and in the little dot that you see there that has a 93% underneath it, what that means is that 93% of the time somebody introduces, somebody tweets about something, and nobody pays any attention to it. Right? So if that reflects your experience with Twitter, then you are in good company. 5% of the time, one of your followers retweets it. That's what the second motif shows you. 0.9% of the time, 2 of your followers retweet it. 0.3% of the time, 3 of your followers retweet it. And 0.3% of the time, you see something that looks a little bit like contagion, where one of your followers retweets it, and then one of their followers, who's not one of your followers, retweets it. So you can also see that about almost 99% roughly of all the events that we looked at on Twitter are accounted for by these 5 structures. And that pattern applies very generally across all 6 of the domains. And in fact, there are, there's 5 slots in 6 domains, so there's 30 possible structures that we might have seen. We only see 7. So there is dramatic similarity across all of these different domains. And in fact, we can summarize even further by lumping everything together and make the following sort of gross generalization, that about 90% of the time nothing happens. There are 0 additional adoptions. About 8% of the time you get 1 additional adoption. 1% of the time you get 2 additional adoptions. And everything else, every viral video, every internet meme, everything you've ever heard of is in that little blue bar on the far right, which happens about 1% of the time. And so you might say, well, that's sort of interesting. But in that little blue bar are really, really big events, things that are so big that they count more than everything else put together. If we think about biological disease for a second, 100 years ago, roughly was an epidemic that was called the Spanish flu that spread in the aftermath of World War I, towards the end of World War I and in its aftermath. And about 1 billion people got infected in this one event. So, that one event would be in that blue bar, but if you counted all the people who ever got the flu, a large percentage of them would have gotten it in that one event. What we find here is that nothing like that exists in our data, right? So the larger events are not that large. And so we can make a stronger statement that if we look at all adoptions, not just all cascades, but all adoptions, 99% of them are within one hop of the seed. So there's very little in viral spreading. Almost all of it is local. So that's the first finding. And if you're like some of our colleagues, when they read about this, they said, okay, you just didn't look at the interesting stuff, right? Like yes, you looked at a bunch of different examples, but we know that there are viral things out there. We know that there are huge viral events because look, we have Gangnam Style, and billions of people have looked at this video. This thing is really a viral event. But the question is it a viral event? Is it a viral event or is it just a popular event? And what's the difference between these two? So, the Super Bowl is a very popular event. Right? About 100 million people watch the Super Bowl every year. But no one would describe the Super Bowl as a viral hit, right? It's a broadcast event. There's a single hub that everybody goes to and watches. They're all watching the same channel and getting the same information at the same time. No one is sort of passing it around. So if we look at something like the Super Bowl, it looks like something on the right-hand side here where you have a single node that's blasting out the same information to everybody and almost nothing else is really happening. On the left-hand side, we have the original picture that represents what we sort of think is going on when we say something is going viral. And so what we would like to do in this project is try to differentiate between these two structural explanations of popularity. And so this is work with Sharad Goyal and also with Ashton Anderson, who's a postdoc in MSR New York, and Jake Hoffman, one of my colleagues at Microsoft. And so a few years ago, we took a much larger data set, a much larger set of Twitter data, in this case over 1 billion observations of people, again, tweeting URLs. So this is looking at the actual content of a tweet where we've taken, in effect, every story, image, news story, image, video, or petition posted to Twitter over the course of an entire year. So if something is going viral, then we will see it. Now, of course, most of this stuff is not really intended to go viral. It could be just people posting stuff for their friends. It could be a lot of really low-quality stuff. So to exclude all of that noise, we restrict this billion-plus observations only to events that got at least 100 retweets. Okay, so this is already way more popular than anything I showed you on the previous slide. So this is roughly speaking 1 in 3,000 events gets 100 retweets. So very, very rare. But because we have over 1 billion observations to start with, we still have 350,000 of these rare events. And so now that we have this selection of popular, of large cascades, we can measure this property that we call structural virality. And so the idea is very simple. I mean, there are other ways to do this. This is not there's no sort of unique, nothing unique about this definition. But the way that we quantify structural virality is we treat every cascade. So let the thing spread. Eventually it stops. And now you have this pattern that's been this structure that's been sort of illuminated in some sense by the spread of a particular tweet. And you can treat that as a network, and then you can compute the shortest path length of that network. So if you have something that looks like a broadcast, the average path length is very close to 2, and so that is the lower limit of what we call structural virality. And then if you have something that's a branching, a multi-generational branching network, then the depth of that network is proportional to the log of the number of nodes in it. And so the shortest path length is also proportional to the log of n. And so for every cascade, you can now compute some number between 2 and log n. And then we do that for all 350,000 of these events. And now we can ask, with what kind of diversity do we see? Is it the case that large events tend to look like broadcasts, or is it the case that they tend to look viral, or is there some sort of magical combination of the two that generates optimal spreading? And then, in addition to this diversity question, we can also look at how this changes as a function of size. So as things get more popular, do they become more broadcasty or more viral? So to answer the first question, whatever you thought you might see, you're going to see it. That there is, in fact, really incredible diversity of structure in this world. We see things that are extremely broadcasty, like up on the top left-hand corner. The big black triangle there, I think this is a CNN story. And so CNN is the CNN Twitter handle is the node at the top, and then you have about 100 people retweeting this, and then very little else happening. And then as you go across to the right and in the bottom row, you see structures that are increasingly viral. And so what's a little bit surprising about this picture is that all of these structures have roughly the same number of nodes in them. All of these things are about the same popularity. But they clearly are structurally very different. Something very different is going on in all of these different pictures. And the other thing to note is that if you look at these little inserts, this shows you, what you would have gotten if you'd just been counting retweets as a function of time. And so you can see that this aggregate measure is not really telling you anything about the structure. So there's no way you could, the only one that looks even slightly different is this one in the bottom in the middle. Everything else looks more or less the same. So nothing about the time scale, nothing about the popularity, nothing about the shape of these curves would really clue you into the diversity of the structure. You have to actually look at the individual level data itself. And then the second question is, well, how does this structure, this diversity of structure vary as you look at increasingly popular things? And the surprising answer is that it doesn't really vary that much, right? That as you go from large but not that large cascades, so cascades in the order of 100, up to cascades of the order of thousands, you can see that for pictures and videos, there's essentially no correlation at all. That the median, which is the black lines here, the median structural virality, first of all, stays relatively constant, and second is pretty close to the minimal value. So what this is showing you is that as these cascades, the size of a cascade is essentially driven by the size of the largest broadcast within that cascade. So this is what we used to call a Justin Bieber effect, because at the time we did this, Justin Bieber was the most followed person on Twitter. I think he's since been passed by Katy Perry or somebody. These individuals have tens of millions of followers. They are essentially broadcast networks of their own. And if one of them latches onto something, they can give it they can really generate a huge number of additional retweets. And so that dependency is what is sort of keeping these cascades going. So in some sense, nothing is really going viral in the way that we imagine it. Everything is kind of dying out in a sub-viral way or a subcritical way. And then occasionally, they're getting these boosts from one of these highly followed individuals. So given that, you might wonder, well, can we predict any of this? What are these, if we sort of believe that, probably the content matters, we believe that the person involved matters, maybe the person who initiates a cascade matters in particular, can we take this information and make some sort of prediction? So we see here an example of Neil deGrasse Tyson tweeting about Einstein. I don't know, is this an interesting tweet? Would you retweet this? Well, 21,000 people retweeted this thing. So you might wonder, well, could you have predicted that? Is there something about Neil deGrasse Tyson that would lead you to suspect it would get this many retweets? There's something about the topic. What could you? What are the features of this tweet that generated that result? And could you have predicted it beforehand? And so this is essentially the question that we set out to answer in this project, again with Jake Hoffman and Ashton Anderson, and now also with Amit Sharma, another postdoc at Microsoft, and Travis Martin, who was an intern with us last summer. And so we're going to really take an empirical approach to this, which is to say we want to see if we can predict how many retweets a particular tweet will get. Again, we're focusing on tweets that contain URLs because these things are relatively easy to classify. We're going to restrict ourselves to the 100 most popular domains on Twitter. So these are, all the things that you've heard of, like YouTube, New York Times, Instagram. So a bunch of media companies, a bunch of video and image applications. And you can also notice that these numbers keep going up. Like every year you look at Twitter, it's increased dramatically in size. So now we have almost 1 billion tweets in a month rather than over a year. So there's been an enormous increase in scale in this period of time. And we have a lot of features. There's a lot of things we can measure now. So we have all kinds of metadata that gets extracted by Microsoft when we ingest the Twitter fire hose, and we have a classification system, and we know things about the location of the tweet and so on. We can also run a topic model over these tweets and have another way of understanding what the tweet is about. We can do the same thing for users using the lists that they're listed on. We can count their followers, their friends. We can measure the past success both of the piece of content, if this thing has been introduced many times in the past, how well has it done previously. We can also quantify that for the users who introduce the tweet. And then we can do interactions between all of these things, right? So we have a lot of features that we can generate. And so now we can construct a series of models that go from very sort of simple and relatively uninformed up to very complex and sophisticated. And we can also do this using linear regression. We can do this using regression trees, and we can do this using random forests. And because random forests work the best, I'm just going to show those results. The question then is, as we sort of go through this sequence of models, how much better does our prediction get? So presumably at the simplest level, it's pretty bad, but does it just keep increasing linearly? Does it asymptote? If so, where does it asymptote? And the result is that, well, there's a couple of things you can learn from this. First of all, you might think that content really matters. It seems like it really should matter. The interesting stuff spreads and boring stuff doesn't. If that's true, we cannot find it, right? The content features tell you almost nothing. The user features do much more. In particular, the more followers you have, the more, on average, the more retweets you're likely to get. So user features tell us a lot, relatively speaking. But nothing else really matters. one of the points that people always brought up when I gave an earlier version of this presentation was that, well, maybe content doesn't matter on its own, but surely the interaction between the content and the person matters. That, people who are experts in machine learning posting about machine learning are more likely to get retweeted than when they're posting about, riding bicycles or something, right? This seems like such an obvious thing, and yet, once again, it turns out, that it has no marginal impact on performance at all. Strikingly, one feature does about as good as all the other features put together, and this is just how successful have you been in the past. So if I have historical data on you, I can essentially predict that you will be about as successful in the future as you've been in the past, and that very, very simple model does about as well as anything else.
Okay.
Yes?
So the graph is not adding features, it's features individually. So in the x-axis.
Yeah, it's a little weird. You're adding features as you go from basic to content past success, and then you kind of reset and start with user features, and so now you have a different set of models here, and then here you're now putting it all together, right? So it's not exactly sort of it's a little misleading, but this dotted line shows you what you would have gotten if you just included this feature and nothing else.
So that means that there is an interaction between user and past success, or it's just past success of the user as
It's not an interaction effect. It is an additional feature. Yes. Right. So if you just sort of could see, oh, I have the metadata for the user, and now I can classify them according to the kind of stuff that they tend to be expert on, because this is how they've been categorized by other Twitter users. That will get you these two increases, and then past success gets you a large marginal improvement, right? But past marginal success would have gotten you all of that way on its own if you didn't have these features. So there's collinearity between all of this stuff, right? Larry, yes.
Yeah, so wondering the topic modeling might be kind of a weak assessment of the content. I'm thinking about like Donald Trump's tweets during the campaign. Some of them came from him, and they were incendiary, and some of them came from the staff, and they were anodized with the tweets. And I don't know anything about this, but I'm willing to guess that the ones that he actually tweeted got a lot more play than the stuff that was like ran.
So there's absolutely, and there's certainly room for more different and more creative ways of extracting features, and it's possible that the human mind is capable of picking up subtleties that are very difficult to capture in any of these models. So thank you for bringing that up. That is the response that is inevitable is that there's some other feature in there, right? That if you could just quantify that feature, that would give you a large incremental boost. Or if you just had a better model, like maybe if you threw some like neural network at this thing, it would do better than random forests. So it's very difficult to do this. You can never really sort of defeat this argument empirically, because you can just keep trying things, and there could always be something that you didn't try. So what we did something else, which is we just sort of simulated an ideal world in which, in some sense, we know everything. Right? And it's a very simple world, and it has two parameters: this reproductive rate, which quantifies everything about how the thing is spreading, and the degree of the initial seed. And it turns out that if you have zero noise and you have zero heterogeneity, so everything is exactly the same appeal, then you can do pretty well. You can get an R squared that is sort of getting close to 1. Although interestingly, it's never 1. But if you introduce any kind of noise whatsoever, or any kind of heterogeneity whatsoever, as soon as you move away from that ultra simplistic, idealized world of perfect information, then the best R squared you can get drops dramatically. Interestingly, pretty close to what we find empirically. So I think there's sort of kind of converging evidence here that getting above R squared of 0.4 is going to be extremely challenging. So what do we learn from all of this? you know, we're learning that even though the vast majority of the theoretical literature that is applied to things spreading in the social world comes from biological epidemics, and that much of this theoretical attention has been paid to the conditions under which things go viral, like what is the tipping point, what is the epidemic threshold. And if you're in marketing, you want things to be above the epidemic threshold, and if you're in epidemiology, you want it to be below the epidemic threshold. But the conditions are like, what is this threshold? Everything we see is below the threshold, right? That there is no sort of, nothing is really going viral in this classical sense. Most stuff stops 1 degree from the node. Even the big stuff is dying out in some sense, but is only being boosted by the scale-free nature of the Twitter graph. And your ability to predict this is also, as a result, subject to some fundamental limit. So I think this, you know, that kind of forcing the theories to engage with this type of data generates new insights that that can push forward the modeling, but also I think the applications. And finally, I think as much as the big data hype has been overplayed in some respects, sometimes it really matters. Sometimes you really need to have an enormous amount of data in order to draw conclusions. So I'm pushing my luck here on time, but I will now talk about the second thing that I want to talk about, which is moving away from big data, moving away from observations, going back to this long-standing model that comes originally from psychology and more recently from economics of trying to learn about human behavior, not by looking out in the world, but by constructing very idealized conditions in a laboratory and bringing people in and having them interact with each other in some way. There are lots of advantages to this. You can answer the question that you're interested in rather than the question that the data allows you to answer. You have a lot of control. You can identify causality or causal mechanisms much more easily. But there are a lot of limitations that come from this model, most of which sort of add up to a lack of external validity. That there are things that we can sort of have people play games, have people play Prisoner's Dilemma in a lab. It doesn't necessarily tell us why they're doing what they're doing out in the world, where all sorts of other things are going on. We can have people solve problems in a lab, but it's hard to generalize what we learn to things that are happening in the real world, where all kinds of other things are going on. WEIRD, by the way, is an acronym which stands for White, Educated, Industrialized, Rich Democracies. So this is sort of, the vast majority of subjects that come into psychology labs are undergraduate students at universities like this one, and they're not necessarily representative of the larger population, let alone the global population. And finally, we can only run experiments for as long as you can trap a bunch of undergraduates in a lab, right? You can't hold them there for a month. Well, I guess there was one experiment where they tried to do that, and we can't do those experiments anymore. So we have to sort of rethink, and is there something that we can do now that that allows us to break down some of these constraints? And I think that this is something that I find really exciting. That we can, if we think about, where is the world in this design space? We have these sort of three stylized axes here of scale, duration, and realism. And the real world is out here somewhere where we have large numbers of people interacting in complicated ways over long periods of time. And all of experimental social science is right down here near the origin, where we have very simple interactions between a few people happening for a short period of time. And the question is, can we push this design space out? Or push the boundary out in design space? So I'll just quickly give you some examples. The first one is an old one. This is work done way back when at Columbia with Matt Selganic and Peter Dodds, where we took 14,000 teenagers and brought them into a virtual lab environment and had them listen to songs. We had 48 songs by bands that they hadn't heard of. And some of them just got the names of the bands in the song, so they just had to kind of play around and decide what they liked on their own. And others got this social signal, this information about how many times these songs had been downloaded before them. And so what we showed with this relatively simple setup is that when people know what other people like, two things happen. First, inequality increases. So popular things become more popular, unpopular things become less popular. But the second thing is that the outcome becomes increasingly unpredictable. So it becomes increasingly more difficult to predict which particular thing is going to become popular. So we see things like information cascades sweeping through these markets, which are in some sense constructing people's preferences at the same time as revealing them. So this was a relatively surprising to many and somewhat deep result that came out of this very simple experiment. But it could only work because of the large number of people, right? That each market, in a sense, required hundreds of people to participate in it. And to be able to make these comparisons, we had to have many markets. So you need thousands of people. And then if you want to vary the experimental conditions, you need tens of thousands of people. So there are certain kinds of questions we might think of as macro-sociological questions that by design have to have many thousands of participants. So you just simply cannot do this in a physical lab. A second kind of constraint that we've been trying to relax is that of realism. That many of the questions that we study in lab settings are highly stylized because we want to test a theory. And so we simplify and simplify and simplify until we have some something that we can actually get people to do in a lab environment. What we studied here is a real-world activity. This is what is called crisis mapping. It's something that has been growing in prominence since about 2010, when a group of volunteers got together and in the aftermath of the Haiti earthquake and extracted from social media and other types of media on-the-ground reports of damage and fatalities and injuries, and created a map that was extremely useful to the crisis responders like the UN. And so crisis mapping is now a thing. There's a whole international community of people who do crisis mapping. And what we did in this experiment is we brought crisis mapping into a lab, and we have a group of people, in this case about 16 people from Mechanical Turk, recruited from Mechanical Turk, brought into this artificial environment. This is work done with Andrew Mao, a postdoc at Microsoft, who built this remarkable piece of software, and also Winter Mason and Sid Suri. And these are real tweets that we got from the Standby Task Force, which is one of the main crisis mapping organizations, that were collected by the task force during a typhoon, Typhoon Pablo, that hit the Philippines in December 2012. Most of these tweets are just sort of people talking about the typhoon. They're not really very specific to anything. But a small minority of them have very useful information in them. And so their job is to extract the useful information, to classify it in this spreadsheet here, and to geolocate the tweets on a map, which is not necessarily trivial because they're not geotagged. They have to sort of figure it out from what the person is saying or the picture or whatever. So a fair bit of sleuthing is involved to geolocate some of these things. So they're basically doing, not basically, they are exactly doing what the Standby Task Force had to do in the real deployment. This is a very real-world task. They're interacting with each other. They're trying to figure out, they're trying to solve problems. They don't necessarily know what they're doing. They have to educate each other. So all of this is happening in real time, and we're measuring everything. And the results are surprisingly good. That in 1 hour in 2014, 16 Turkers came up with a map that was actually about as good as the map that the task force itself came up with over the course of 24 hours in 2012. So the question that we were interested in at the time was, how big should this group be? do 16 Turkers the right number? Is 32 Turkers the right number? Is 2 Turkers the right number? So we can, by varying the size of the group, we ran dozens of these experiments. The task was always the same. And we're able to characterize performance as a function of size. And so, I don't have time to go into the details right now, but I'll just note one thing, that these largest groups up here of size 32 are doing about as well as the standby task force itself. So this is the dotted red line. So all kinds of interesting things that one can learn about group problem solving by studying like realistic tasks. And then finally, and just quickly, I want to talk about a very recent experiment also done with Andrew Mao and Sid Suri, and also Lily Dworkin, who was an intern a couple of summers ago, where we went back to one of these very simple stylized tasks. So why would we do prisoner's dilemma? It's not very realistic. It only involves 2 people, so there's no scale here. There's no complexity. But there's an interesting puzzle nonetheless, which is that when people play a finitely repeated game of PD against each other, something like this tends to happen. They start off cooperating, and then they get to the end of the game, and somebody defects. Because they're thinking, well, the game's about to end. I might as well try to cash in my chips. And then that causes the other person to defect in retaliation. And so the question that is interesting to us is, well, what happens if we do this over and over again? Do they sort of keep playing the same way? Do they come to an understanding and cooperate the whole time? Or do they get increasingly cynical? And do you see cooperation unraveling such that eventually you get no cooperation at all? And it's the last hypothesis that is the dominant one in the literature. And there's sort of partial evidence in favor of it. But the problem has always been that there's not enough time. That you bring people in, you have them play 20 of these games in a row, and you see a little tiny bit of unraveling, but then you have to stop, right? And so whatever the time scale is on which this unraveling happens, it's much longer than you can keep undergraduates or even MBA students in a lab for. So what we did is we ran exactly the kind of experiment that people have been running for many years, but instead of running it once over one day, we ran it 20 different times over 20 consecutive weekdays. So this is the same group of people coming back over and over again every day for 20 consecutive days. And just to show you what that looks like, this is the game that I just showed you. This is, and then they keep playing for this. They're being randomly reassigned to other partners across several games. This is what one session looks like. You have 50 pairs of people, so 100 people playing 20 games. So this takes about 40 minutes to do. And then this is what the whole experiment looked like. So this is 375,000 actions over the course of a calendar month. So what do we see when we get this kind of data? Well, we see something very interesting, that there is support for the unraveling hypothesis that in the later rounds of the game, the rounds 9 and 10, you see cooperation is dropping dramatically for several days. But after several days, it stops and remains stable. And the reason is that about 40% of the people, and so 60% of the people in this population behave like the theory suggests, that they are essentially rational, and when someone exploits them, they become more cynical and they're more likely to defect earlier on the next round. But then everybody kind of does that, and they start driving each other backwards. But there's about 40% of people who just aren't like that. They just, for whatever reason, decide that they're not going to change. They're not learning, whatever. Maybe they're altruists, we don't really know. But they are what we call resilient cooperators, and they just keep doing the same thing over and over again. And they have the effect of anchoring the other players so that they stop this unraveling. And so you see remarkably high cooperation levels persist for essentially the whole time. And what's also interesting is that these cooperators are paying a price for this. So they are, in some sense, sacrificing their own payoff in order to keep the entire population at a high level of cooperation. The point I want to make here is that you could not have seen this if you could only run an experiment for a day, right? It took about 7 days for the stabilization to happen, to show up. And so And so the point is that if we want to use experiments to understand real-world social processes, we have to be able to run experiments for real-world, that last for the timescale of the real-world social process. Okay, so I have some sort of wrap-up slides about what we could do, what we need to do in computational social science. I'm really out of time, so I'll just summarize and say, really three things. We have to think hard about observational data. That it's wonderful that the world has kind of given us this gift of things like Facebook and Twitter that generate data for us that we can then go and study. But that model provides real limitations because the data essentially was not generated for the purpose of answering social science questions. And so it's possible that we have to go and build our own instruments and we have to collect our own data. Although we have to find creative ways of pulling together data from different platforms, whereas currently it's very much siloed into individual platforms. A second problem is that, or second challenge, is that these virtual lab experiments that I've been talking about, there's sort of one point example where we do a simple thing for a long period of time. There's another point example where we do a complicated thing for a short period of time. And there's another example where we do a simple thing with a lot of people. We haven't been able to figure out how to do all of these things at once. And so there are sort of big logistical challenges to constructing, and technical challenges to constructing virtual lab experiments that can be run in a more lightweight way to really sort of explore more of this design space. And then the final thing is that I think this stuff is fantastically interesting, and I love working on these little toy problems and writing about them, and I think that that's one way that social science can contribute to the world is just by sort of investigating puzzles and explaining them to people and helping them to sort of understand that the world is more interesting and complicated than they might have realized. But in some sense, is not enough, right? That if we want to go from science to policy, if we think that the kinds of things that we do as social scientists matter to the world, that we care about, facilitating reasoned conversation in public discourse. We care about reducing inequality. We care about reducing systemic risk in financial systems. That we care about making organizations more efficient or teams perform better. There are real practical problems out there in the world that are, in a sense, social science problems. And if all we do is write papers and publish them in journals, I feel like, in some sense, we're not doing enough. And so one great opportunity, I believe, for computational social science is that by its nature, it is more amenable to some of these real-world problems. And so a final challenge for us is not just sort of improve our methodology. It's not just get more and more ambitious with our research designs, but it's also let's think very hard about the impact that we're trying to have in the world of business and policy and the things that ultimately kind of got us into doing social science in the first place. And so with that, I will say thank you very much.
All right, yeah, thank you. I think we have time for a few questions.
So I'm really interested in the relationship between popularity and viralness.
Yep.
And I'm curious if there's if popularity kind of seeds the conditions for something to go viral. Like it is not sufficient, but it's necessary in order to seed the host to be a good, carrier. So it's not the same, but you need the popularity.
So the question is, that sufficient conditions are hard to identify, but maybe necessary conditions are possible for things to spread. I mean, I would say that in this case, necessary conditions are also difficult to identify. I mean, look, we can get an R squared of 0.4, right? So it's not like everything is completely unpredictable, but most of most of what turns out to be useful in these models is sort of very kind of simplistic stuff like how many followers do you have, and so that itself, of course, is a complicated product of all sorts of other things that were going on, right? So there's a reason why when Donald Trump gets a lot of retweets, it's not necessarily because he's doing something interesting on Twitter. It's because he's a famous person who's going to be our next president, in the rest of the world, and so his impact on Twitter is in some sense a reflection of the interest that the world has in him generally. And the same applies to to celebrities. You could say, well, not everyone can have 80 million followers on Twitter, right? It's not you have to have some other source of visibility or influence. So. So in some ways, you could say yes. There are necessary conditions, like which are things like number of followers you have or past success and so on. But then if you try to unpack those become you sort of go down the rabbit hole of, well, how did that happen and how did those people become successful? So I think the answer is we can make reasonable predictions, given data that we can pick up at a certain point in time. But I don't know that we can answer sort of meaningful questions about, like, what are the necessary conditions for success.
So I don't want to get passed on, but so not just like the number of followers, but the nature of those followers.
I was wondering about with respect to virtual labs, the extent to which there's going to be, is Microsoft involved in any infrastructure research, developing things beyond MTurk? So all of our virtual lab work is really dependent upon that infrastructure, and I just wondered to what extent that ecosystem is going to
reminding me of that. Where are we? This is this is not a Microsoft-specific project, but Andrew Mao, the postdoc who I mentioned, has developed this software called Turk Server, which is based on the Meteor platform. And so this is an open source project that you can install an instance of it on your own server, and it has a bunch of nice features that allow you to recruit people from Turk, pay them, manage, create multiple experimental conditions, randomize people between them. It handles all of the back-end data storage in Mongo, and provides also tools for building front-end interfaces for the subjects to interact with each other and with the experiment. So it's not a sort of out-of-the-box solution to an arbitrary experimental design, but it's a lot better than trying to do it on your own. And so I think one thing that we hope is that this, either this project or some project like it will attract an active community of developers and experimentalists who are contributing software and improving the software and making it, reducing the barriers to entry so that it becomes, right now it's still the case that in order to do a behavioral science experiment, you have to be a pretty good engineer, or you have to be paying someone who is a good engineer. And so this sort of prevents a lot of people who might have very good ideas from running experiments. And so I think it's important that that we also, as a community, focus on building tools that make running experiments easy. And if a company like Microsoft devotes engineers to helping, that's that's great, but I think it's fundamentally a community of people that we need to bring in. So thank you for bringing that up. I think this is there are other projects out there as well, and it's not clear to me yet which one will become sort of the Linux of online virtual lab experiments. But my hope is that one of them does.
Yeah, I'm wondering what the implications are, the first part of your talk, for a person who's trying to get a message out with a fixed budget. And presumably, the cost of acquisition of some of these big influencers is much higher than the cost of acquisition of, the small. So I don't know if there's some ratio, that tells you, how you should invest your limited budget to get the message out, and whether there's empirical evidence for that ratio being roughly the same across many different kinds of messages. And
So we looked at that question, hypothetically in an earlier paper in 2011, and we concluded that. So it was a very simple model where we looked at, there was just the sort of there was some fixed cost associated with running your campaign, for example, and then there's a sort of per user cost, which is what you have to pay to recruit one of these Twitter users. And there are actually there are agencies now that represent people like the Kardashians and other celebrities that in effect charge you according to how many users followers the person has. This study was motivated by a story that I read back in about 2009 about Kim Kardashian charging $10,000 to tweet about a product. She probably charges a lot more than that now. And so I was asking exactly this question: is that the right number? She had about 1 million followers at the time. She probably has tens of millions now. Maybe that's the best way to spend your money. Or maybe you'd rather, recruit 1 million people with 10 followers and pay them, a dollar each or something, right? So what we were able to show with this modeling exercise is that under most conditions, you actually wanted to recruit a large number of relatively unknown people. There's a sort of a diminishing returns to followers. So even though these big people do in fact have more impact, their impact is sublinear, whereas the cost of recruiting them is linear. So, of course, this is all just a theoretical model, right? So the thing you really want to do is do the experiment, do the field experiment, and we have really thought about that, but unfortunately, the Twitter APIs are not designed, we can't do it. Like, just mechanically, it's impossible to run that experiment. So this is, going back to this question about, Twitter wasn't designed to do social science. I think it's a great question. It would be interesting to answer. Maybe we have to build our own instruments to answer this sort of question. Right?
So it's very exciting to see the way you've been able to quantify the difference, for example, between popularity and virality. But of course, when you're looking at data that's being transmitted digitally, so you're looking at Twitter, you're looking at Facebook, what happens each time it passes on, it hops from one tweet to another tweet. It is identical. So because you're dealing with a digital signal, each time there's no variation. And that seems to me to be, to place a real limitation on thinking of these diffusions through Twitter or through Facebook as a model for social diffusion where each hop introduces variation. So, a virus or speech and language data, as a word goes along, it diffuses through a society.
Yeah, I understand.
Each node adds something that you don't get when you look at this digital model.
Yeah, so it's a good point, and in fact, we were relying on that particular feature for the work that we were doing. That we wanted to sort of skirt the problem that you just brought up by picking. The reason why we study URLs is precisely because they don't change. So it just makes things very easy to track. Now there has been other work Yuri Leskovets at Stanford, and Lada Adamic at Facebook have both done interesting work where they try to address exactly the concern that you raised, where they look at they reconstruct these like philological trees of memes, so they can detect that that a word has been substituted, or that an image has been altered, and so they can reconstruct the whole mutating cascade. And so I think that would be you would get a more complete picture of what was really happening, and it would be more relevant to things like natural language tweets rather than tweets that involve URLs. All of that, I think, is useful, productive work that people should do. I would bet that it's not going to change any of these results. I think you'll get different headline numbers, but the qualitative results will stay the same. But that's just my prediction.
All right, let's thank Duncan again for the wonderful lecture.